Very good morning. Hi everyone. Welcome back to this educational platform. Let's look at today what we're going to do. I'm planning to go through a evaluation of an integral. The integral that you might have seen or you haven't seen as of now. But still, you can get some kind of a rough idea or loosely look at this integral. This is I equals it's going to go from stand for the integral minus infinity to plus infinity of e minus x squared dx. See? This is the integral I'm mindful. I want to get this done. If by as of now you have learned that integrals involving with exponentials, exponential with e to the x only, or sometimes here you have a certain function, but along with that one, right next to that e to this exponent component, you're going to have like a derivative of the exponent. That exponent's derivative would pretty much easily tackle because the way that it's been structured. But unfortunately, we don't have the derivative of minus x squared, which is minus 2x, right next to this exponent. You see, this exponential function, it's not there. So that means that tells us very clearly that there's no way that we can use the integration by parts, change of variable technique, or using differential technique, or using use substitution. So those 3 or 4 methods cannot be utilized or employed in order to get this done. Now we have like a greater question ahead of us. If that's the case, how we could gonna solve this one? How we gonna evaluate this heavy integral? Do we have any other ways of getting this done? Yes, we have 2 ways of getting this done. The first one using the statistical distributional properties. The other one using the polar coordinates. In this class, as of now or up to now, we haven't covered polar coordinates. We are planning to cover polar coordinates pretty soon down the road before semester finishes. But since we haven't gone through polar coordinates, some student might have seen this polar coordinates, some student might have heard about polar coordinates, some student might have worked with polar coordinates, but not everybody. Since that everybody haven't seen this one, I'm planning to just get into the second method, which is the using the statistical distributional properties and get this integral done. Okay, I know that everyone who has taken, anybody who has taken any type of basic stat courses have heard about the normal distribution. Normal distribution is very symmetric, bell shape, and it's going to go from minus infinity to plus infinity to with its own domain, with the different shapes, with its different peakedness. It's completely based on the value of the standard deviation and the average of that particular distribution. So let's look at this one. Let's look at the shape of the normal distribution. In the normal distribution, see, looks like a bell-shaped distribution. See, continuation being denoted by 3 ellipses or 3 dots. It's going to start from minus infinity and going to go to plus infinity. See, having an axis of symmetry. At the axis of symmetry, you have the mean. Mean is located at that point, which is denoted by mu. This letter is mu. A lowercase Greek letter. Excuse me. Greek letter to denote the average of this distribution. This is called normal distribution. Normal distribution. Or some people call this one Gaussian. It has been named after the greatest mathematician Carl Gauss, who invented this particular distribution. And on this axis we have x, on this axis we have f of x. This is a very special function. We don't call that one function. We're going to call this one probability density function. Probability density function. Instead of talking about that regular function that's available in mathematics, we're going to call this one probability density function with a certain property. What's the property? How come a regular function become a probability density function? Probability function having like a area under the curve is always 1. If you have any function and its area under the curve over its domain is 1, that particular function simply becomes a probability density function. So therefore, I'm going to call this one probability density function for sure. This normal distribution is a statistical distribution which represent or which just give like a graphical representation of the probabilities. Probabilities cannot exceed more than 1. In that sense, its area is the probability. If that's the case, probability, since probability is 1, we can definitely say that this is a probability density function, because if you calculate the area under the curve of this particular function over its domain, which is negative infinity to positive infinity, that becomes 1. So this is a probability density function. Probability density function. It's being abbreviated as PDF. What's its formula? Its formula is nothing but 1 over 2 pi square root 2 pi sigma, something called sigma. See, this is called sigma. It's another lowercase Greek letter to denote standard deviation. And e to the minus half x minus mu over sigma squared. See, that's the formula. So on the other hand, the distance from here to this point and distance from here to, I haven't drawn this on the scale, but it should be symmetric, bell shape. This is symmetric about mu and bell shaped. That distance is referred to as this is one of the point of inflection of this particular function. See, there's another point of inflection on this side. That distance from here to here is sigma. That's the standard deviation. I'm going to denote that by SD. See, sigma, SD, standard deviation. I'm going to call this one SD. Abbreviation, standard deviation, abbreviation is SD. You see? So we know the name of the distribution, normal distribution. We know the properties of that one, which is symmetric and bell-shaped. We know these properties, these distances. We know the equation. If you get the area under this curve, which is always 1. So what we're going to do, that means area, I'm going to write here, area under the normal curve, this one we can say normal curve, over minus infinity to plus infinity is 1, always 1. Then area is nothing but the integral. It's nothing but the integral. Integral of the function. Okay. So integral of the function. That means this means nothing but integral going from minus infinity to plus infinity f of x dx, which is 1. See? Then minus infinity to plus infinity is nothing but 1 over square root 2 pi sigma e to the minus half x minus mu over sigma whole thing squared dx equals 1. See? Then we can pull out this constant 1 over 2 pi square root sigma minus infinity to plus infinity e to the minus half x minus mu over sigma whole thing squared dx equals 1. See, looks like we are heading towards what we really need, but we don't have what we really need. This is my integral. I is minus infinity plus infinity e to the negative x squared dx. See, this is my integral, but I don't have it. That means with some adjustment into this integral that I have over here, I can get what I really need. What kind of adjustment I have to do? See, here there's no mu. See, let, I'm going to say let mu equals 0, and sigma has to be how much? This whole thing. See, 2 sigma squared has to be 1. See, has to be 1. From this one you can easily get sigma. Sigma squared is 1 over half, and sigma is 1/2. We're going to take into account on the positive part. You see, let's plug in this one back into this one. 1 2 pi square root sigma is nothing but 1 over square root 2 integral minus infinity plus infinity e minus, you don't have, see, minus half x minus 0. See, 2 sigma squared is how much? Whole thing 2 sigma squared. This one is squared, is 1 dx. See? See, like that. So here we can see cancel out 1 over pi square root pi negative infinity plus infinity e minus x squared dx equals 1. Here equals 1. This is nothing but I. See, 1 over square root pi equals 1. Therefore, I is nothing but this is going to bring to this side root pi times 1, which is root pi. Therefore, you can say I equals negative infinity to positive infinity e to the negative x squared dx is root pi. See, root pi. That's what I need. So that's the answer of that integral. Thank you very much. See you next time.